underwater. Underwater means below the draft line. For extreme case, rectangular pontoon can be a block coefficient is 1. You may think about barge. Barge is like a pontoon. And Great Lakes bulk carrier. Do you know where are the Great Lakes? Yes? No? Where are Great Lakes? Yes. Yes. No. Yes or no? So why don't you raise your hand then? No, right? How about you? North America. Right. Right. Where is it? Yes. Where is the US? Where inside the US? You don't know. Right? They are saying where I between US and Canada. Right. You're right. Right. In the Midwest, they are saying Midwest, but it's where where is the Chicago? Chicago, Illinois. Yes. And Chicago is not near, beside the lake. You know that there is a beach along the Chicago city? Yes, you see from the film. That is the Lake of Michigan. Great Lakes is made of 5 big lakes. Biggest one is the Michigan Lake. Is at the side. So Michigan Lake, the west coast beach of the Michigan Lake is Chicago. Right? West and south corner. Right. And the right-hand side of the Michigan Lake is the state of Michigan. And inside the state of Michigan, there is a city called Detroit. I explained about Detroit, right? No? Detroit is a main city for automotive industry, right? Biggest 3 automotive industry inside America, United States is, what are they? Big 3 automaker of USA. Ford.
Ford is like inside one big company that includes Chevrolet, Ford, Cadillac, General Motors.
General Motors. Ford. Chrysler. Chrysler is now merged into, not now, 10 years ago, merged into Daimler of Germany. Merged Chrysler, right? So now it's Daimler Chrysler. And 3 of them, biggest automaker of the United States, their headquarters is located in Detroit. That's why Detroit is the center of automotive industry, right? Because there are so many raw material around Great Lakes, and also at that time, 120 years ago, transportation is mainly by ship rather than car or train. 120 years ago, transportation, mainly ship along the Great Lakes. That's why the location of Detroit was good for automotive industry, because Detroit is south end of the Michigan state and boundary of the Great Lakes, because that is good for transportation through the Great Lakes and also good for sales to the mainland body of United States, to the east. At that time, East Coast, Chicago and New York and Washington, there's a main customers are there. So once again, Great Lakes bulk carriers. Why? Because they need to pass through canal between lakes. Between lakes. Great Lakes is made of five. Right? Five. But Detroit is located in which lake? Not Michigan Lake. Michigan Lake is uh, Michigan is looks like the state land state is looks like this way. And Michigan Lake is here, and west side there is a Chicago, but Detroit is in this corner, the land side. So there is another smaller lake, 80, right? Still big, but among Great Lake. So the raw material is coming from the north side through the ship, but ship should pass through the canal between lakes. And then once again, Suez Canal, Panamax, right? That's why they have a limitation of breadth, but they want to transport more cargo. So their shape is very long, long. Breadth is limitation, right? Instead, they have a longer. So the block coefficient is fullness. Because it is long, middle body is almost box shaped. Only end part is ship shaped. So block coefficient is elongated. Coefficient is grows higher. Right? That's why they have a 0.9. But the problem is they are slender, right? So that bending moment is very high, and weakness of midsection is. Question? Only because it is possible because Great Lakes, though the wave is not so big as Atlantic or Pacific, so that even though they are slender and long, the bending stress is allowable at that position. So there has a special shaped bulk carriers there. And oceanographic research vessel, it is smaller ship comparing to the cargo ships. So very smaller ships usually has a no middle body, no parallel middle body. We say parallel middle body means Great Lakes almost 80% is same shape, box shaped. Only end portion, 10% is ship shaped, right? But smaller ship, fishing boat, there is no parallel body, right? Front and end, that's it. So that's why they have a lower block coefficient. And definition, so high CB, usually it is low speed because it's a fat, but it is good for cargo capacity, right? But it is low CB means slender or low resistance. So yeah, high speed and good for sea keeping. Sea keeping means in the wave, the ship is moving, but if you have you remember that warship coming from the Japan to the Korea, right? They are slender and good for sea keeping. So this is the definition. Volume of the ship, but only on the body, underwater body. Draft. There is above her, but it is cut off. And LBT T is the box, underwater body box, right? And then divided by volume of displaced water, right? So we can say this is a displacement. Right. So you may see that there is also above water body, right? Above water body, but that is not calculated for the CB. all including superstructure and also a deck, main deck, and other hatch cover. So, but now calculation is only for underwater body. Midship section coefficient. There is a maximum section coefficient. CX is midship section coefficient, and AX is underwater. Also again, underwater area, right? Underwater area. Midship section, but only underwater section, not above water. And then divided by B multiplied by T. And prismatic coefficient is another one. So they are saying M or X. Sometimes they are saying M. M means a midship section. X means a maximum sectional area. For a long ship, midship section is long, or parallel mid body is long, so that midship section is okay. But for the, say, yacht, sailing yacht, do you know how it looks like, sailing yacht? Usually they have a sharp front, but back side is bigger to the back side. So that midship section is not so maximum area. Maximum area goes toward a little bit behind the midship in case of sailing yacht. That's why they divided into two different CM and CX is different for the small ships. Right? But big ships, CX is same as CM. Prismatic coefficient is divided by AX rather than BT. Right? So graphically looks almost same, but difference is this corner. The denominator is not LT, but LAX. So this is a prismatic coefficient. But we care about this coefficient because of it gives you more different property of the ship. And waterplane coefficient, this is not volume. This is based on area. Waterplane area, this is a highlighted one in cutoff of draft line. So that is waterplane area over there. Waterplane area, and divided by this the square, or not square, rectangle. With this is a waterplane area coefficient. This is important for hydrostatic spring. Spring is, you remember this is F kx in spring, right? Mass and spring dynamics, right? And when you, this is x, right? X, and this is k. When you pull down the spring by 1 centimeter, then you have a force, right? Multiplied by spring constant, right? Depending on the material of this spring, K is fixed, right? And then you release, then it is oscillating, right? You already learned about this one, right? Oscillation. Now, ship, if you push down the ship by 1 centimeter down, then you need to have a force, right? When ship is floating, this ship is floating, right? In this way, we need to have a, sometime we need a waterway. Right. Let's say next Wednesday, we will class at Eureka Building. Is it okay, right? You don't have a class on Wednesday. Right. Next Wednesday, we will have a class on Eureka Building because there are experimental facilities there. Right. So I want to show you. So it is floating. If you push down 1 centimeter down, you need to have a force to make it down further, right? At the equilibrium position, you need to push down, right? And then release. Then it come back, right? Come back. Same mechanism like this. So we call this is a hydrostatic spring. Hydrostatic spring. And spring constant is related with area. This area, water plane area. Because we push down 1 centimeter down, the area and 1 centimeter volume is displaced. Displaced water. Force is same as displaced water. Right? So I push down 1 centimeter by force. That force is response of displaced water. So the spring, same as spring. Response is not so fast like this one, but slow, but still same mechanism. Right? So we call it hydrostatic spring. Spring constant. Speed, Froude number. Right? Have you heard about Froude number? Yes? No? Yes? All right. How about Reynolds number? Yes? Yes? A long time ago. You heard about this, right? What is the difference between Froude number and Reynolds number then? Eh? Both are non-dimensionalized number, right? To measure speed somehow, right? Yes? No? Yeah. Yes. Somehow they want to measure speed related to something by using non-dimensionalized coefficient way. Right? So we'll see. I don't remember this. Probably force. One is force, so it's related with viscosity. Viscosity is related to the area based. The other one is inertia. Inertia is based on mass, right? So it's a volume and area. That is a difference, but we will see next time. Anyway, one of them is Froude number. So for the ship designer, I want to see whether the ship should be faster, but there is usually have a requirement by the owner, right? I want this ship should be speed of 20 knot or 30 knot. Navy usually want to have a high speed combat ship, right? But anyway, for the contract, we need to have a requirement for minimum speed 20 knot. Then I should design myself to good ship design, right? As a designer, right? But minimum requirement is 20 knot for this big ship. Then how should I prepare the engine? What should be the horsepower for that engine? And what can be the propeller for the ship to maintain 20 knot? That is my mission. I should calculate, estimate, and then show them, prove them. This is so that usually you need to have a little bit higher engine power, a little bit higher target speed, a little bit higher, not much higher, right? But that is my capability as a designer, right? But it's not easy, right? But anyway, that's why we are using Froude number and Reynolds number in all this. So at the beginning, they use this way, speed and length ratio. Somehow, as a designer, I collected many design cases, good design cases, and plot as a curve. So they use this one, speed length ratio curve. And that gives you this square root, not, and that gives you some kind of trend. That's why they use that kind of parameter rather than length breadth ratio or block coefficient or others. Right? Speed length ratio was. They found that there are some correlation between parameters. As a designer, I want to find out what can be my ship, right? And at the trend. So I plotted. But now this is not a non-dimensional parameter. So in old days they used this one, but at the somehow they found that this one is better. Right? This one is better because it can be length can be meter or can be feet. Is a meter per second? It can be a knot per second or knot per hour, mile, or right. So sometimes it's confusion. Right? So that's why they want to have a non-dimensionalized some parameter. So Reynolds number and Froude number is coming. Naval vessel 35 knots is very high in ship as a ship. So Froude number is 0.45. But if you lower down the speed as a 10 instead of 35, Froude number is only 0.13. But 150 is a smaller ship. 500 smaller ship, right? Smaller ship, research vessel, 10 knots gives you Froude number in this way. 10 knots, 10 knots, Froude number is different. I show you this difference because you found out that big ship is easy to have a higher speed because it is a ratio, right? Ratio. It is a natural trend. So big bird can fly faster than smaller bird. Right? Fly. So big airplane is good for economy. Higher speed and less. Higher speed means less resistance per ton. Right? So that's you need less engine power comparing to per passenger. Question? Proportion. Other parameters they plotted many different ways. Right? Length depth ratio they found that this is good parameter for structural design, the midship section design. Right? Length beam ratio is good for maneuverability. Maneuverability is this way. Maneuverability. Right? There is also parameter whether this ship is good for maneuverability or not. How about your car? Do you have a? You don't have a car now. Do you have a driver license? Oh, all of you. So you have an experience, right? So which car is good for maneuverability? Sports car, right? Sports car is good usually, right? Why? Why? It's a complicated one, right? Anyway, I want to measure as a number. Its car or ship is good for maneuverability, right? Good for handling or driving. Right? But they use LOB for as a parameter for plotting all the ships statistics. Length draft ratio, bow slamming. Bow slamming means when the wave is coming, ship is pitching, and then wave hitting the water surface when they come back, right? In this way, come back, pitching. Because of the wave, ship is moving in this way, right? We call this is pitching. And then slamming is water is slammed to the bow, bottom of the bow. So that usually can create damage during severe weather. The hull, the plate is bending or break. Beam draft ratio, stability, right? Stability. But transverse stability means capsizing, right? When you, so sports car again, you make a high speed turn, right? With a cargo truck with a high cargo, it's not stable, right? If you turn stiff, then the truck can be capsized, right? But the sports car is good for cornering, right? They are not capsized when you have make a hard turn. So that we call this is stability, transverse stability for ship. Right? Similar, right? Ship is when you make a turn, hard turn, the ship can be inclined, but there is also restoring force, right? But depending on the ship status, some ships are very unstable, similar to high cargo truck. Right? You should be more curious, slow, soft turn. Right? So beam draft ratio, wave making characteristics, wave making. When ship is moving into the water, there is a wave coming, generated by the ship. Right? Have you experienced that some ships are some crossing each other, and then wave is generated by another ship. My ship is moving in this way. Right? There is a wave made by ship. Right? And you can say that wave is, you need to make a wave, you need energy spent to generate wave. Right? So that we call wave resistance. Wave making lose energy, so that we call this wave generating resistance. Who you asked about the bulb. I explained the cosine and sine. So wave making, canceling, so that their idea is no wave generation loss. Right? So that is a way. And CB divided by L over B, maneuverability again. Optimization. So depending on, so this is a fat ship, you can say fat, but this one is very thin and slender. So this is maybe good for what is it? Wave seaworthiness. Or did I mention sea navigation? Where is it? I explained all of this. Seakeeping. Okay, seakeeping. Seakeeping. So slender ship can be good for seakeeping. The similar to Japan ship. This is similar to Korean turtle ship. Right? So this one, the left one is slow speed. Right one should be faster. Right? So L over B, length breadth ratio. This is a low speed cargo ships, tanker, oil tanker, bulk carrier, 17 knot, 16 knot, 15 knot, length breadth ratio, and resistance in, what is it? PERC? I don't know. Percentage? Yeah, percentage. Looks like a percentage. So that if you increase length breadth ratio, that means slender, right? Slender. Length breadth ratio. Length breadth ratio. Increase is slender, right? Slim. That means your resistance is lower down, right? Lower down at the same speed. Container ships, reefer means a refrigerator container. refrigerator container ship. 23 knot, 21 knot, 19 knot. So usually comparing to the ship type, container ships is higher speed. Right? Cruiser, ferry, cruise ship, 23, similar, right? Similar. But anyway, you see that all trend is length breadth ratio increase, slender, thinner, resistance is lower. That means higher. Fullness is a block coefficient, right? And that this one block coefficient, and this is a speed length ratio. Speed length ratio, but a little bit different. Is a acceleration by gravity is invited, so that they try to make it non-dimensionalized. The Froude number, something like that, right? Can you remember this Froude number? Where is Froude number? Froude number, right? G is here, right? So this is Froude number. Speed length ratio almost same, but only G is coming, right? So that is non-dimensionalized. So this is a Froude number. And then as a designer, I collected many good ship designs and dimensions and make a plot. So the statistics, and they found there is a trend, right? Trend curve. And then they make this curve as an equation like this one. This is equation. And then as a designer, I use at the beginning this equation for my ship. Right? So I choose that my ship will be around 0.65, right? 0.65. Equation is same again, same equation. And then it can be this way. Oh, choose 0.7. And then speed length ratio in this way, right? Or reverse way, right? Because I want to make a speed as fixed as 25 knot, and length can be coming from another equation. Then it should be block coefficient can be in this way, vice versa. That is the way designers are doing, finding out the main dimensions. Hull form, lines drawing, general approach, techniques. This same is mold loft. There is a picture, right? Old picture. When, say, 100 years ago, this one, what is it, this one? This one is one section of the ship. One section, this curve. One section of the ship. Do you know how to make a yacht? Material? What is the material for making yacht? Plastic. Looks like a plastic. Right. We call it FRP. What is the FRP? Right. Say again, louder. Fiber, reinforced, plastic. So plastic, plastic. But reinforced by fiber. Which fiber? Which kind of fiber? Glass wool, something, right? Glass wool. So when you make a FRP ship, boat, yacht, you need a fiber wool fabric, very similar to this one. Looks different, but fabric, right? Cotton. You cut and then put them shaping, and then looks like a painting of plastic, resin. They call it resin, right? The smell is not good, but anyway. And then it's very similar. So for me as a body, I want to make a ship looks like my body. Then they cut similar to making this one, put on my body, and then plus resin painted. And one more layer, resin painted. One more layer, resin paint. But you need a time to hardening that plus resin, right? So it takes time. But anyway, in this way. At final stage, you need the painting, real painting. For this, you need some kind of body, right, to put on. So body should be very fine shape of ship. This is one of the station shape. So you need this kind of how do you call this one? Form or baseline curve, 20 part or 40 parts as you want, right? Make that kind of stational sectional curves and making them and putting together as arranged. And then you need also make in between you need to have some kind of plywood attached on the cover. And then you find the final skin of the ship, wood ship. And on top of them, you start to grasswool, resin, grasswool, resin. That's the way we are making a sailing yacht. Right? It takes time. Right? It's not easy. In old days, you need to do this real scale curves of each section of the ship. They did 100 years ago. Now, no more. They do by computer. So there is a technology you need to learn about this. All right. So this is a three-dimensional surface, freeform surface. Airplane, car, automotive car also, right? Three-dimensional surface, right? Freeform, right? Good shaping. But you need to make this one out of flat surface plate, right? Airplane, automotive, ship, all of them. The final product is three-dimensional freeform surface, but you making them based on two-dimensional flat plate. You cut, glass wool is same, right? You cut and shaping and then gathering together, putting together, joining or welding. So it is complicated. So series of two-dimensional contour means contour curves from parallel cross-section. Cartographers is geography, map, constant elevation, right? Slicing of fish, same. So this is more dropped. So this is a geographical sectional curves, right? Sectional curves, same as sectional curves. And this one is we call lines drawing, body plan, shear plane, half breadth plane. Half breadth plane is together. It can be a water plane. And this one is sectional curves, right? This one, sectional curve. And mold draft, you make this one, putting together and making them between, and then putting FRP glass walls. And this one is the one of the main drawing I told you, lines drawing. What are the three main drawings? Okay. What are the three main drawings for ship design? General arrangement, lines. Midship section drawing. For the structure. So this is a lines drawing, one of the main, right? And we call this is a body plan, vertical plane, water plane lines. And this one is body plane, water plane, shear plane is vertical lines. Same one but different name, shear plane or vertical line. Right. And main dimension, length, what is LOA? Full name of LOA? What is LOA? Nobody knows? Ah, length overall. Length overall. LVP? Length? Hmm? I explained about AP and FP. Between two P, this is LVP. Right? FP, AP, and between P, length between perpendiculars, LBP. And FP is 4 peak, all 4 perpendicular. And AP is after peak or after perpendicular. Breadth, depth, and displacement. Somebody should calculate this one. When I was a student, this one is given to me, and then I should make a 3D surface using paper, paper ship. Same as shipyard. Shipyard making ship out of steel plate. Instead of paper, using these drawings, they build ship. Same as me as a student, I cut off papers and somehow putting together, making ship. Right? Outer surface, not internal, outer surface. And video. Okay. We can do discussion next time.
Designing something like the hull of a ship can be an expensive process. So how do you rigorously test out a design before you even build it? A unique research program at the University of Iowa makes that possible using sophisticated software, model ships, and an enormous indoor pool. The University of Iowa's Ship Hydrodynamics program, the home of this high-tech facility.
These are called wave basins. You can see the wave makers at the far end here. They're prototype. They go up and down. They generate either regular or irregular waves in the basin.
Here's a ship, and they are pitching in the wave. This is a wave.
The next part for us then is the carriage. This is a custom designed carriage. It follows the model. There's targets on the model that the cameras and the tracking system use.
This is maneuvering, turning, right?
It's
Turning.
designed specifically to carry measurement systems to measure the local flows around the free-running model.
This is a Navy ship.
Believe it or not, this nearly $5 million facility was designed
Stealth,
and built
stealth
primarily
Navy
for
ship,
the purpose of
stealth.
validating or testing computer code.
Propeller.
That code, CFD Ship Iowa, is a simulation software developed at the University of Iowa for the Office of Naval Research. In the past, Stern and his research team validated the code by running their models in a 300-foot-long towing tank. But as computer power grew and the code became able to do more advanced simulations, so it required a more sophisticated tool for validating.
Our code developed very rapidly over the last, really, 5 to 10 years, to the point that we were able to predict the exact trajectory of the model, including rudders and rotating propellers, and no longer restricted to passive simulation. Therefore, to validate it, we needed to see, well, how accurate by trajectories that being modeled, for example, going, you start up to your head, you give the rudder a 35-degree angle, and it's going to go in a circle. We want to know what's the radius of that circle. Another type is a zigzag path where you put the rudder 10, 10, 20, 20, and then you predict it's going to be overshoot. There's half a dozen or so of these traditional tests, both in calm water and waves, that ships have to be able to demonstrate the
Capsizing
performance
of the ship.
satisfactory standards in order to be built. And so our focus is not actually design. Our focus is development of the tools.
While the wave basin will enable new advances in hydrodynamics, Professor Stern says it indicates the direction much of science is already heading.
The future of engineering is simulation-based design. And in fact, we can simulate things we can't measure. So you begin to see a major shift in the scientific method, where we went from Aristotle, okay, who based everything on logic. He didn't bother to, he thought men and women had different number of teeth in their mouth. For my favorite story, but of course they don't. And he could have figured that out easily by just looking in his wife's mouth. But it's kind of looking at his teeth, but no, logic, some logic, and no doubt the future of engineering is simulation.
Professor Stern says it.
Right. The ship's shape is a little bit different from ordinary ship. Can you see? They are developing a stealth ship. What is stealth? Means? What is the meaning of stealth? Undetected by what? By radar. Right. For the airplane, mainly, right? But they are also developing a ship for undetected by radar. They call stealth ship. Developing in this way. Right. The shape difference is they have a narrow above water structure, superstructure, in this way, so that radar is come back, go in the other direction. The older ships, they have a flare in this way because of the wave coming that reflect, and also superstructure is box shaped for the as a resistance space, right? Simpler to build, right? But radar is detecting, so that they want to make this way, and smaller, lower, and in this way, so that radar is going bounced away. Right? But problem is stability. That's why they're testing stability. So stealth is one good capability, but stability is the requirement. So there is one. Okay, too long. Well, anyway, go on to